Hi everyone, and welcome to another uh, video for Chapter 16, Thermal Energy and Heat. So what I want to do with this chapter is go over, if you have your textbook, you can follow along with section 16.1. I'm just going to highlight some of the key concepts in this chapter. If you want to know what you should be able to do by the end of the video, well, you should be able to explain heat and work, explain how heat and work transfer energy. You should be able to relate thermal energy to the motion of particles that make up a material. You should be able to relate temperature to thermal energy and to thermal expansion. And hopefully we should get into calculating thermal energy, temperature change, or mass using what's called the specific heat equation. And then we'll talk a little bit about calorimetry. We might save that for the class though, because that's what we're going to be doing in class for the lab. Okay, so here we are. We've got your chapter starts off talking about Count Rumford, who was a person who supervised the drilling of brass cannons in a factory. And the reason in the 1700s why he gets a mention in your textbook is that at this point most scientists thought that heat was a fluid. They thought heat was matter that kind of flowed between objects. And well, in 1798, this guy, Benjamin Thompson, also known as Count Rumford, really had a different idea. And what he noticed was that when he made, in the process of drilling holes for cannons, he noticed that when this process was occurring, that the water, that this process, the drilling of the holes, would occur in water, and the water would boil so that the metal wouldn't melt due to the heat produced. And he discovered that once he stopped drilling, the heat wasn't around, and therefore the water stopped boiling. So you realize that if the water stopped boiling when the drills stopped drilling, that whatever was making the water boil was no longer present. And that got him into thinking that heat was not a form of matter, but a form of energy that exists when work is done, the drilling of the drill. Okay, so we get also into work and heat. Some of the work done by the drill, getting back to, him drilling in those holes for the cannon, um, is useful work. Some of them actually, drilled the holes, but some energy is lost due to friction, which is the rubbing of the two surfaces, the drill and the cannonball. So anytime work is being done, some energy is always lost due to the rubbing of two surfaces. Now, when you have two surfaces that are a different temperature, you also have the transfer of thermal energy, which is known as heat. And we also know, we investigated in class, that this transfer of heat occurs spontaneously from hotter objects to colder objects. And that can really happen. Heat can be transferred really one of three ways, either through conduction, convection, or radiation, which we'll get into a little bit in the next couple sections. So we have this idea of heat being transferred from hot or cold objects, and we know that temperature is a measure of how hot or cold an object is, and that needs to be compared to a reference point. We can also get temperature, can also be defined as related to the average kinetic energy of the particles, how fast or slow they're moving. And don't forget, all matter is in motion. Whether it's a solid, liquid, or gas, those molecules, those little lumps are dancing for you. They are moving around. They have an internal energy due to how far apart they are from each other and due to their motion, how fast they're moving. So we say that all matter has this internal energy. As an object is heated, that internal energy can be increased by those particles moving faster on average, because every particle has a different speed associated with it. So that's why we say on average. Okay, so that brings us to, what is this internal energy that I'm referring to? Well, it's thermal energy. Let's give it another name. Thermal energy, the energy internal to an object or within an object is the total potential and kinetic energy of all of the particles of an object. And that's really important for you to remember, that temperature is just how fast the particles are moving. But thermal energy takes into consideration not only how fast they're moving, but how many particles there are. So we say that thermal energy depends on mass. Thermal energy depends on not only the mass, but the temperature and also the phase, because how fast the particles are moving will determine whether or not the material is in a solid, liquid, or gas phase. If they're in a gas phase, guess what? Those particles are moving really fast, and they have a certain distance between them, and they're free to move. So, and we'll talk a little bit about that when we talk about phase changes, when we get into our next chapter, when we talk a little bit more about matter. Okay, so here we have getting back to thermal energy. And one of the questions on your next quiz or your next test will sound something like this, which is, which of the following, an iceberg or a cup of coffee, has more thermal energy? If we could quantify it, if we could give it a number, which one do you think would have more thermal energy? Remembering that thermal energy is not only dependent on temperature, how fast those particles are moving, but how many particles there are. So, think about that for a minute. Pause the video and think about it. Go ahead, pause it. Okay, now hopefully you thought about it, and one of the things that I remember thinking about when I had this question for the first time was, let's assume your iceberg is freezing. And if it's freezing, it's at 0 degrees Celsius or 270 degrees Kelvin. And if you're wondering what's Kelvin, go back to the last video. It's just another way of measuring the average kinetic energy of a substance. It's a different temperature scale. Okay, so 270 degrees Kelvin, or degrees, or yes, or 0 degrees Celsius. Okay, so now imagine your cup of coffee might be something like 75 degrees. And if your coffee cup is 75 degrees, which is about 350 Kelvin, well, 350 isn't a whole lot more than 270. So if we take that temperature difference, yeah, well, the coffee has a greater temperature, but when we remember that thermal energy also deals with how many particles there are, and an iceberg is 1,000 times larger than a cup of coffee, you guessed it, that even though the iceberg is at a lower temperature, it contains a whole lot more thermal energy because it's not at absolute zero, and it's much larger than a coffee cup. So it does have a value, and there's many of those there's many particles with that value. So we get a greater thermal energy value. Another way to think about it, girls, is that a cup of coffee has more thermal energy per unit of volume, but an iceberg has more thermal energy overall. Okay? Another way to think of it, because I like to give it to you a couple different ways, is this. What would happen if you poured a coffee cup, if you poured that coffee on the iceberg? Which would change more in temperature, the iceberg or the coffee? Yeah, you got it, the coffee. That's because the iceberg has a greater thermal energy than the coffee. Okay, so next I want to talk to you a little bit about thermal contraction, which is a consequence of a change in kinetic energy. And how do you change kinetic energy? Well, you change the amount of heat being transferred into that object. So slower particles, which have less kinetic energy, they're going to collide less often, and they're going to hit they're going to hit each other with less force. So the pressure decreases, and that object contracts. Those particles get closer together because they're slowing down. Think of it like when you're at a mixer and somebody puts on a slow song. All of a sudden, everybody stops dancing quickly and they start to slow down. And unfortunately for the chaperones, you guys might get a little closer together. Okay, so this is called thermal contraction. And you can see this also when you take a balloon outside on a really cold day. Your balloon, the volume of the balloon decreases because the pressure at which those helium molecules are hitting the sides of the balloon, the inside of the balloon, has decreased, so your balloon doesn't have the same volume. it has contracted. Those molecules within the balloon have contracted, have gotten closer together. And it's called thermal contraction. Okay. Next we have thermal expansion, which is when there is an increase in the volume of the material. So the material is getting, the volume is getting larger, and that also may be due to a temperature increase, or the average kinetic energy of the particles are increasing. So how does that happen? Well, again, heat it up, and that will cause the particles to increase in kinetic energy, and thus, collide more often, hit the walls of the container more frequently and with more force, and that will cause the material to expand. Gases expand more than liquids, and liquids usually expand more than solids because, remember, they have the space to do so. And we'll get into that when we talk more about properties of solids, liquids, and gases. Oh my. Okay. Thermal expansion, another example of that would be what's used in the thermometers. As the temperature increases, the alcohol or mercury in the tube expands, and the height of the column of the volume of the liquid inside the thermometer increases. Okay. I think I just have enough time to introduce you to this concept of specific heat, and then I'll do another video that talks more about the mathematical model associated with it. Specific heat is a concept that we give to the amount of heat needed to raise the temperature of 1 gram of material by 1 degree Celsius. Now, that's what it sounds like to me. So specific heat, I need you to go think about your everyday experiences, which is if it's a really hot day and you touch metal, that metal's going to be really flippin' hot. Whereas opposed if you walk over to a tree trunk and you touch the tree trunk, that wood will not be as hot. Even though they're absorbing the same amount of heat, there's a difference in how quickly and how easily the temperature of the substance will rise. So the lower the material specific heat, the more its temperature rises when a given amount of energy, heat, is absorbed by a given mass. Fancy way of saying that different materials will absorb heat, and that heat will change the temperature of the substance differently. So when you think of metals, metals have low specific heats because their temperature rises so easily, and that's why they're such good conductors. Whereas plastic usually has a higher specific heat relative to metals, and that's why we use plastic as insulators when we cook, because they resist these temperature rises. It takes more energy, heat energy, to change their temperature for a given mass. Okay, so I think that's all we have time for right now. So I'll do the next video on calculating specific heat and setting us up for the calorimetry lab.